Hello, good morning. I'm Wenxiong Li from NAOC. Professor Weimin Yuan, the PI of EP, cannot make this trip, so he let me to present this talk for him. But he is online, so he can still answer questions after the talk. I will talk about exploring the transient X-ray with Einstein Probe. I will first provide some background for the X-ray transient science and introduce Einstein Probe and its science capabilities. Then I will present some selected interesting discoveries of transients by EP, and finally make some comments about how EP can fit into the future landscape of transient. So this is a plot that what transient phenomenon we can study with non-X-ray observations. So for the massive star core collapse supernova, in optical we can see the supernova, and we can study the radioactive decay and the kinetic energy. And it can also produce a gamma ray radiation. And the gamma ray is powered by a very strong jet. And the binary neutron star merger can also produce a gamma ray burst. And in optical infrared UV, we can see the kilonova phenomenon. And it's also radiating the gravitational wave. And for black hole tidal disruption event in optical, we can see the reprocessing and the non-relativistic events. And with X-ray, what we can learn is that if we have X-ray for the massive star core collapse event, we can see something between supernova and gamma ray burst, such as choked or failed jet, and weak jet, weaker than the strong jet by the from the gamma ray burst, and shock breakout. And for the binary neutron star, we can see X-ray counterpart of the binary neutron star merger, and it may be powered by the central engine. And for the TDE events, we can also see longer timescale X-ray events, and also powered by the different central engine. And besides EP, there are already some operative X-ray all-sky monitors, but they all have different shortages, such as non-focusing, or have lower sensitivity and lower spatial resolution, and some of them do not. Many of them do not cover the soft X-ray large field of view. So EP used this lobster eye micropole optics, which was proposed by Dr. Roger Andrew. So with this technology, we can do the focusing imaging while keeping the large field of view. So EP take advantage of this technology and integrated into this wide field X-ray telescope. The WXT has 12 modules. So each one has 4 CMOS detectors. So you can see the 12 modules is around the center. And in total, it can reach 3,800 square degrees in one exposure. That's basically about 9% of the whole sky. And the source localization can reach 2 to 3 arcminutes. And in the center, we can see 2 follow-up X-ray telescopes. The wavelength coverage is wider, and also it has much higher sensitivity and has much better localization. And this is a collaboration between China, ESA, and Germany. And for data transfer, EP can have fast satellite to ground two-way communication in minutes, including fast alerts and fast TOO observation commands. And this is achieved by China's Beidou system and VHF network, which was introduced before, and to do the science data telemetry. This is a collaboration between China, ESA, and France. And EP was launched 2024, January 9th. The formal science operation begins at that July, which is exactly 2 years ago. So from these 2 images, we can see the EP and the SWIFT, their weight is comparable. So this is the WXT first light image. So it's basically the first soft X-ray focusing imaging with very large field of view. And this is the soft X-ray spectrum of Cas A during the calibration phase. So EP has several observation modes. The survey mode is by the WXT, so it has very large field of view, so you can do the survey to discover transients. And the FXT can perform autonomous follow-up observations, and it can also perform TOO observations by the upload. For the WXT survey, it has 3 pointings per orbit, and every pointing is about 1,000 seconds. And the night sky can be covered in three orbits. And in the meantime, the FXT can perform its own observations for those pre-selected targets or TO targets. So this is the coverage demonstration for the WXT survey. And this is the sensitivity of EP. It's much higher than the previous all-sky X-ray monitors. And this is the on-orbit results that confirm the EP sensitivity in different exposure time. And one important feature of EP that it can, the WXT and the FXT can coordinate. So such as the WXT detect transients on board, and it can send the alerts downlink to the EP size center in NAOC in Beijing and automatically send out the GCN notice. At the same time, the FXT can get that information, so it will point automatically to this force. So if there's still a signal, we can get much deeper image and a much higher localization information. So with the better localization, it's reached to 5 to 8 arcseconds. Then we can perform multi-wavelengths like optical near infrared follow-up observations. So for this event, we can see the green circle is EP FXT position error. And here, finally, you find the optical transient. So it's small enough. There will not be so many optical transients. And this is the EP transient in the first 2 years. In total, it's discovered more than 230 X-ray transients and issued more than 400 GCN and ETEL reports. And there are more than 100 transients have optical counterparts, and 55 we have redshift measurements. And for classes, we have fast X-ray transients, TDEs, compact object flares, or other unknown classes. And this is the sky distribution of this transit. So you can see there are many types, some interesting like jetted TDEs and supernova, and some new types. So now we go to the science. So what's the core science of EP? EP is aimed to detect the systematic survey of transients and source variability in the soft X-ray with very high sensitivity and cadence. And also to discover normally quiescent black holes and other compact objects by capturing their transient X-ray flares. And also try to detect and localize the potential X-ray sources of gravitational wave events. And I will give some example of this discovery. For the extragalactic fast X-ray transients, EP has discovered around 180 of them. And 1/3 of them are X-ray flashes, and 1/3 of them are GRB in soft X-ray. And at least 9, we have supernova associations. But there are only several before EP, which has this supernova association. And it is starting to find previously predicted or unknown phenomena, and to probe the diversity of collapsers and compact binary mergers. So this is a plot to show that the time scale for the soft X-ray and the gamma ray for the GRB events. So the dashed line shows the 2 time scales equal to each other. We can see the soft X-ray time scales basically all like greater than the gamma ray time scale for the prompt emission of GRB. So that means the X-ray durators may different from GRB, but before EP we don't have the capability to detect the prompt emission of soft X-ray of GRB. So this is a statistic work, ongoing work, try to capture this feature. And now, next I introduce some individual cases. The first one is not discovered by EP, it's discovered by Liang, and in 2023. Liang is the EP Pathfinder mission. It onboards experiment satellite, and it's basically one module of the WXT. So remember, the WXT have 12 modules, so there's only one module. The field of view is much smaller, and it was operating between 2022 to 2025 and retires after EP operation began. And during the Liang operation, this event, the LXT 230307A, is an X-ray transient likely powered by binary neutron star merger. In the left panel here, we can see the signal from Liang and GECO-LAM. GECO-LAM is a hard X-ray and gamma ray burst detector. The red one is from Liang. So we see the Liang light curve is much flatter, and the time scale is much longer compared to the hard X-ray and gamma ray signals. So that's a hint that they may come from different origin. The higher energy may come from a GRB jet, and the lower energy soft X-ray band may come from a magnetar-powered origin. Another evidence is from this panel. So this is the SED evolution of this event from the early phase to later phases. And the authors did the broken power law fit to the soft X-ray and the hard X-ray and gamma ray like separately. And the dashed line and the dotted line here is they try to extrapolate the two fits to each other. So you can see they deviate very significantly. That means they are not cannot be fit by a single fit. So there's another evidence that they are from maybe different origin. And in the later time, the gamma ray and the hard X-ray basically disappear, and the soft X-ray is still visible. Consistently is basically the information from this panel. So this source detect the soft X-ray likely powered by a magnetar and the jet. The higher energy made from a jet. And the magnetar is emerging from the burst onset, the compact binary merger burst. And there is another work by JWST. So the authors found a kilonova signature from the JWST spectrum. So that confirms or consistent with the Liang and the GECO-LAM result. And now we have more FXT events that also have this possible merger origin, such as this several events. So that's before EP, this is the Liang mission. For EP, the first one I want to introduce is this EP 240414A. It's possibly a new type of fast X transit associated with supernova. So the optical counterpart of this source is a type 1c broadline supernova. And from this plot, this is the so-called Amati relation of GRB. So it's the peak energy in KeV versus the isotropic energy of the prompt emission. And here is this event. It's deviated from the common relation of the GRB. That means the X-ray spectrum of this event is very soft. The peak energy is very low. We only have the upper limit of it. So we didn't measure the exact value of it. So from the optical observations, it can be divided to 3 parts in the first 20 days, like 30 days, 20 days. And the first part is the first decay, which is the afterglow of the jet. And the third part is very similar to a classic type 1c broadline supernova. And the most interesting part is the second part, which there is a rebrightening in the optical band. And we can see it's very bright. It's about minus 22 magnitude. And we propose that this is the shock cooling emission from the expanding, extended shell. So combine the X-ray and the multi-wavelength observation together, we think it's the brightness of the X-ray is similar to the low luminosity GRBs and much brighter than the classic supernova breakout. This is the supernova breakout curve. This is the new event. But the soft X-ray, the X-ray spectrum is very soft, so very distinct. It's different from the low luminosity GRB. So together we propose is a weak relativistic jet that interacts with an extended shell surrounding the progenitor star. And this is a cartoon we make, EPSC make with a company, and I made it with the Chinese AI video model, the C-dance, to show the evolution of this event. So in the beginning, we have a star exploding in the center, and here is the purple one, the CSM, and we have the jet, a weak jet from the two polars, and after the explosion, the shock will come out, interact with the CSM shell, and this brightening is what we see in the second bump here, and the jet is also disappeared after, so we detect the X-ray from the jet, and the jet disappeared very fast. The next one is a GRB event. It's EP2403158. It's a GRB at redshift about 4.8. The interesting part is that in this panel, the bottom, this longer timescale emission is detected by EP. So it's an X-ray, soft X-ray emission. And the narrow red window here is a gamma ray burst window. So the soft X-ray begins before the gamma ray, but stops after the gamma ray. So it has much longer time scale than the GRB event. And the redshift is confirmed by measured by VLT. And this event for EP, this event can be detectable at much higher redshift. And actually now EP has already detected 6 events that has redshift more than 4. But the problem is how to confirm how to measure the redshift. If it's redshift 7, this event would be very difficult to get the optical or near-infrared spectrum very rapidly because it decays very fast for the optical counterpart. But physically, it's very interesting why we have this prompt emission much longer than the GRB event. So you can see the time scale. The GRB, the T90 is about 40 seconds. And the soft X-ray, the T90 is about 1,000 seconds. And the last one for the fast X-ray transient is this EP241113A, which is we think is a first clear evidence of an energetic dirty fireball in X-ray. If we check the X-ray light curve, it has a steep decay and a plateau, and then there's a break and I go to another decay. So from the plateau to decay, the break, the authors can derive the Lorentz factor of this jet. So they think it's consistent with a jet of Lorentz factor about 20 and viewed on axis. So this is the long-predicted dirty fireball feature, which is a relativistic jet contaminated by baryons. And put it into the RMRT relation again. So this is the supernova one, the EP240414A is here, and this is this target. It's also deviated from the relation. So it's much softer than the RMRT relation. And this is the first evidence of such kind of events. And this conclusion of the fast X-ray transients, we detected many interesting fast X-ray transients. And Professor Brian Schmidt, last month, he made this comment at Turku. He said the classic long-short classification barrier has fundamentally broken down. New data from the Einstein Probe has opened up a previously hidden selection bias universe of soft X-rays and soft X-ray transient and low luminosity, low energy jet, GRB supernova that were completely missed in the SVOM area. So next we go to the TDE. So this is the TDE detected by EP at 2024 February, and it's an off-center one. Or if we compare, related to the large host, it's off-center. It's about 35 kilometer projected distance from the center of a massive galaxy. And there's a very faint host there, and the redshift is measured. So this is the X-ray and optical evolution of this source, and EP detected it, and later there are nicer observations. Okay, yeah. And the optical light curve actually emerged before that. So the time is the same scale. So it's before the X-ray. So after the joint fitting of multi-epoch X-ray observations, the authors derive its the TD by the intermediate black hole. The mass is about this. They fit this with thermal Compton and the slim disk model, get the temperature and get the this black hole. Yeah, this black hole, the mass. And the host, the big host galaxy, the stellar mass is much higher. This paper is under review, but basically like accepted. And the last TDE I want to show is this EP250702A. It's a possible DT of white dwarf by intermediate mass black hole. It has very bright X-ray flash and decay very fast. The faster decay, the shorter time scale makes the author think like they fit the data and think it must come from a white dwarf, might from white dwarf, and they fit the spectrum and also found its extreme relativistic jet at the early time. And the later time, you can see there are two components of the spectrum. One is a black body, one is a power law. So they think at later time, it's the energy is mainly from a thermal disk, and at the early phases, it's powered by relativistic jets. So they think it's a TD of a white dwarf, and the mass they estimate is here. It's 10 to 4 solar mass, so 7 times than that. And the final case is there might be some new transient class. This event is EP240408A. It has a 12-second long, very extreme bright X-ray burst, and has a several-day-long plateau and sharp decay after that. And we don't have optical or near-infrared counterpart. So it's difficult to say what's the nature of it. But the spectral and temporal properties of this event are inconsistent with any known transient types. And besides the individual case sources, because EP has a very wide field of view, so we can get the all sky soft X-ray image from EP. So we are keeping accumulating those data. And for data release, EP has released the first batch of data. You can check that in NADC, NSSDC in China, or ESA's EPSA. That's only include FXT data, the follow-up X-ray data, and the WXT will come soon. And the final comment is that in the EP will keep like detecting, discovering very interesting X-ray transients in the next decade, and it can provide information that cannot be get from other like wavebands. And there will be TOO observations like opened. The test is being tested. And the synergies with multi-wavelengths, multi-messenger is very interesting. And there will be a legacy database for the 3D X-ray sky. And in NLC, we are pushing forward our own multi-wavelength facilities, such as CSST will be launched in 1 year, 2 years. It's a 2-meter wide field space telescope. And for optical near-infrared, we are building this 14.5-meter optical telescope in Western China, and it's fully funded, and it's being built now. And the first light will come in 4 years. And for the GOTA, it's an initiative that we tend to build about 100 1-meter telescopes, wide field globally, basically with BRICS countries and many countries abroad, and also some in China. And now we have built 2 1-meter telescope with 25 square degree field of view. And the FAST will be upgraded. You know, FAST, the resolution, spatial resolution of FAST is not very good. So we are building the small dishes around the FAST, the big disk, to increase the spatial resolution of it. So yeah, that's the summary. I will leave it here. Okay, thank you.
Thank you very much. Thank you very much. If you have questions, comments, there's one. Okay.
Thanks for a really nice talk. For the broadline 1C, I just wondered if you have thoughts on the way the jet is quenched. Is it the reverse shock actually destroys the disk, or how is the jet quenched?
You mean it's failed? For this event, we think it still succeed. But there's another
Yeah,
event
but it goes away, right?
Yeah.
I mean, so how does it destroyed? I mean, we can talk about it all.
Oh, okay.
Yeah. Hello?
It works.
Just talk. Okay. Very nice talk. I want to ask, how do the follow-up X-ray telescope to FXT follow all the triggers of WXT, or the selection triggers to follow?
Yeah, for the autonomous follow-up, it's like if the transient meets some like criteria and it do automatic follow-up, that's like there's no human intervention.
Yeah,
But
yeah.
if the signal to noise is lower, it maybe like cannot trigger the onboard follow-up. And basically, we publish all the autonomous follow-up observations in the GCN circulars.
Ben.
So for a number of these events, you give upper limits on the E peak. But there is also this event where the emission that's seen in the Einstein probe doesn't match the same duration as the emission seen in the higher energy satellites. So I guess as a general question, when you see an EP event and you give an upper limit on the E peak, in how many of those cases can you rule out that there was a gamma ray burst with a higher E peak coincident with it, perhaps on a slightly different time scale that might have had a harder spectrum for the purpose of interpreting something like the dirty fireball candidate?
We like some of the events, we extrapolated the soft X-ray to the hard like gamma ray, and it's just some of them is lower, like lower than the detectability of the gamma ray satellite. But I don't have the statistics here.
Okay.
Oh, yeah.
Yeah, it would be interesting if
there will be a
cases.
sample work on that.
Okay,
Yeah,
good.
that's very interesting to investigate.
No other questions? Online, of course, so you can raise your hand. Asudana?
No, if there are.
No, I've just asked.
Okay. No, this is, I think it's a very good point that meant that it's exactly also when I think about the synergies between EP and SVOM, we have at least one candidate, I think, where we have both that has been detected by EP, but
there are several ones, I think. There are
yeah,
several detected.
at least one
Yeah.
that no, of this one, I mean, of this
Yeah.
let's say soft event where we can constrain very well the EP. But yeah, I think it's a very good comment, and it's powerful. It's the power of working together when we have the same events detected by both.
Hello, I was curious about the time T9D difference. Is there some general picture emerging about it, that the X-ray is coming from any different material or something?
Sorry, which event?
In general,
yeah.
you were shown that T90 is different between the X-ray and the gamma ray emission. So is there some general picture emerging to explain this difference? Is there emission region is different or anything?
Yeah, I think it's complicated. Partly it can be observation bias. Partly it can be like physically different. So yeah, I don't have a short answer for that.
Okay, we thank you again, the speaker. And we welcome the next one. So, coming with his computer. You can take the microphone. Yeah, coming. So, very fine. You have 50 minutes.
Okay. Well, thank you everyone for being here, and thank you for the organizers. My name is Siddharth Chaini. I also go by Sid Chaini. I'm a PhD student at the University of Delaware. Today I'm going to be talking about probabilistic modeling of transient light curves with neural processes. Or that is what I had in my title, but I have a new title, which my pointer is not working. It's okay, that's not there. So yes, I call it Night Lab. And I work a lot with Rubin LSST, so a lot of this talk is targeted towards LSST, but the method I'm presenting is not necessarily strict to it. So let me get more into it. And like I said, I now have this up on archive, so most of my talk is going to be sort of covering everything that's here. Please take a look at the details. I won't be able to go through everything, but if you have questions, I'm always around for the whole week. And so in case you missed it, I'm glad to tell you that exactly 1 week ago, LSST just started. So this beautiful observatory in Chile is now collecting data, and we expect millions of light curves, which for us transient astronomers is awesome, but also challenging because we can't look at each individual light curve, right? So these are just a few of the examples of the different kind of transients we expect to see. And so what this means is that if you don't do machine learning, I just want to tell you how it's being used. So with this volume of data, machine learning is absolutely crucial for a lot of the science we as transient astronomers want to do. And so the way you want to do machine learning then is, firstly, it consists of getting data representations. So that means that if you have a light curve, you want to transform it into some set of numbers, representations, which you can sort of learn from and do machine learning with. So an example of that could be like just fitting an astrophysical feature, right? So just fitting your favorite model to a light curve to get some fits. For example, if you have a supernova, you can do something like a supernova parametric model, and that'll give you some numbers that represent your data. And alternatively, a more popular approach nowadays is also using deep learning. So you can pass the light curve directly to a neural network to, again, get some numbers just to represent your data. So that's part one. After that comes the science. So now you can use machine learning for your specific use case, which could be anything from classification, redshift estimation, systematic searches, population study, anomaly detection. Whatever you want to do, that's you can do once you have these data representations. And just to plug something I'm interested in anomaly detection. So if you also want to chat about that, we can talk. This light curve I showed you earlier is an idealized light curve, right? So this is a simulated light curve in perfect cadence, which is that I have an observation for every day over all 6 bands of LSST. But with LSST, our data is going to be much, much sparser. And if you've already started looking at the alerts, you can see something like this. And so now getting data representations from this is much harder, because now if you use the same fit from before, it suddenly doesn't work that well. So if you don't have data in certain filters, you just cannot make a fit. And even if you do have some data, because of the sparsity, you do get features that do not do a good job representing your data. But what if there was a way we could interpolate and make the light curves better, right? Better for science. And so that's something that's become really popular nowadays, which is interpolating these light curves before either of these. So if you can interpolate light curves well, you can get better data representations, in turn, better science. So it improves everything downstream below. And the most typical approach for us transient astronomers is to use Gaussian processes for this. So you can use a GP regression to interpolate and go from sort of sparse data to and interpolate between time and wavelength and go to much denser representations. But GPs require you to choose a kernel function. And so if now you have a transient you care about whose physics you really understand and know really well, you can do a really good job at choosing a physics-driven kernel because you know how the transient evolves over time, how the color changes over time, and you can choose kernels that encode this information inside it. But in astronomy, we often do not know the physics perfectly. But even if we do, we have to use it on a general transient. So we won't know what the class of an object already is. And so because of that, we sometimes end up using this general kernel, for example, a Matteo 3x2 kernel, which sort of fits a wide variety of different transients and seems to pass the eyeball test. But there is a problem here, is that because the kernel choice depends on the physics, and even if we know the physics, a single kernel cannot work for everything because the physics of all the diverse set of transients is necessarily different. And what this means is that that's why Gaussian processes will never work for every single transient. And another problem with them is also they're very slow the way we use them, and I will talk a slightly bit about that at the end. And so I've been exploring the use of neural processes, which are a family of models that learn distributions over functions, just like GPs, with the help of neural networks. They combine the best of both worlds of a neural network, but also Gaussian processes. Like neural nets, they're fast, but like Gaussian processes, they produce distributions with uncertainties, crucially. And so you can think of them like a Gaussian process where you're learning the kernel with a neural network. And so my goal has been to use neural processes as a better pre-processing step for all LSST transient light curves. My methodology is data-driven, but it does not need to be limited to LSST nor transients, really. But let me now briefly describe what we show in the paper. So I've been using these set of models to model simulated light curves. And my data set consists of a ground truth data set of various different simulations of type 1As, of type 2Ns, 1A91BGs, et cetera, et cetera, et cetera. So I have a ground truth set which consists of dense cadence simulations. I also have a test set which I hide from my model to evaluate it on. And then later on, this is the key thing that differentiates a neural process from regular neural networks, where training involves sampling a small set of points from each dense cadence light curve and training on that. And because of this, over time, the model learns the general structure of the different diverse set of transients. That goes to a neural process model, which can now then produce a model light curve that looks like this. And so this is what reconstruction looks like then. So if you have a light curve where you've only seen the solid points, the model only sees that and can reproduce the full light curve, which is the lines you see on this plot. And the background, the crosses are just the ground truth values, which the model does not see. But you can see that the ground truth value is quite close to the predicted value by the neural process. And I compared this to a bunch of different benchmarks, including Gaussian processes. I should note that they do not really allow for meta-training, which makes the neural process much more powerful. And so you can see that for this particular example, the neural process is doing a much better job of being able to trace out the ground truth value of the light curve. A Gaussian process is, you can see, a bit wonky and does not really capture the different band correlations that well. But that was just one example. How does it perform on a lot of different data? Can we get statistics? I do not have the time to go through all these numbers. So in the paper, we look at a few different metrics, which look at regression, probabilistic uncertainties, and astrophysical features. So things like errors, reconstruction errors, probabilistic, is it well calibrated? And can we recover things like maximum peak, magnitude, and so on? And crucially, the neural process for this set of data performs much, much better on most of these metrics than all other models. And finally, I also want to talk about inference speed. So a problem with Gaussian processes in the way we use them is that if we use a generic kernel, you have to fit them individually to each light curve, which is very, very slow. The neural process model, on the other hand, you only train it once, And then inference consists of a single pass through this neural network. So what that means is that necessarily the neural process is much, much, much faster, like 10,000 times faster than the other methods I mentioned. And because of this, it only takes 1 microsecond per light curve during inference. And so what that means is that for something like Rubin LSST, where we expect around 10 billion alerts a night, processing all of them would take 1 minute. And that's where the name comes from, if you were wondering, nightly light curve analysis with neural processes, or night lamp. And it is a public package, so you can take a look at that. But something I want to end with is LSST is live. It started 1 week ago. And till now, everything was simulations. So in the last 1 week, I've been trying to see and play if I can work with real data. So I've been trying on fine-tuning this model that was trained on simulations, but can we train it on top of that with real data? And I'm seeing some limited success already. And I'm incredibly happy about that. And that is something I'm exploring. So the model seems to be working well. It gets better as you keep adding points. And it works for sort of a different set of transients. These are all from the LSST alert stream. So, but this is still very preliminary, something I'm still playing with. I want to end with this animation, which is why I'm using my own laptop. So if you were wondering why we call it a night lamp, it's because I'm hoping to illuminate the light curves. So thank you. I hope you enjoyed the talk. So just to summarize, I think neural processes are really elegant models for working with light curves. If you are using any kind of light curves with machine learning, I think you can use them in foundation models in whatever task you want. I am moving from simulated light curves to real data with DP2 and alerts. And if you have a transient you particularly care about, let's talk and we can try and hunt for it together. So thank you so much. And I should also add that I will be on the postdoc market soon. So just saying.
Thank you very much.
Thank you very much. Very, very interesting. I was wondering for next steps. So it's you are applying this into a broker, and you will have as output, for example, probabilities linked to a certain classification, or like this can be, I don't know, a kilonova with that percentage of probability, or a supernova 2P with this other percentage, or I don't know.
Yes, thank you. So yes, eventually I want to incorporate it into a broker. Right now, because I've still been working with sort of simulations, it's not production ready yet in some sense. But then the way I envision it is that there will be sort of like probably a base model which just interpolates the light curve, because right now the model does not care about the class. So it automatically sort of gets the right shape based on the data available. But what that means then is that it's probably understanding some physics, right? So it could easily be used to classify as well. So it encodes some information. So right now I have not explicitly ran tests on classification, but I expect something like that to work as well. So in a broker-like setting, I imagine you could see what the predicted light curve is, and then also an associated class based on that. But that's still in the future for now.
Yeah, thank you. I'll be short. When you said fine-tuning on the real observations, you don't know the ground truth, so how do you do it?
Yes, thankfully, or not thankfully, LSST during commissioning took a lot of data points over a particular set of nights. And so I just train it on, like, say, like if I don't have 100 points, I still have 25 points, I can train it on 5 points and ask it to predict the other 20. So although there is less ground truth values, there is still, I can still mask or hide some of them. And because the model is pre-trained, it sort of already knows what to expect in some sense, so you don't need a lot of data for that.
You have partially answered my question already, but you said that you can also run it on 5 points, or like, what is then the minimum cadence that you can imagine? And have you thought of like using it, like combining it with the Atlas data, or like running it on some other things like often afterglows or things that occur on short time scales?
Thank you. Yes, so there is for the model doesn't care about the number of points. You can have 0 points, but then it will just display nothing. In that sense, I would have to sort of take a look and sort of do some calibration tests on, okay, this is when I trust the model to be confident. But crucially, because there are uncertainties, right, you can see that the uncertainties sort of get sharper as you collect more data points. So in that sense, we also found that the calibration, at least on the simulated data, was really good. So the uncertainties seem to do a really good job at capturing when things are sort of under control. So if you don't have a lot of data, automatically you have very large uncertainties. And in terms of connecting it to different sort of data sets, yes, that is also something I've been thinking about, because if I can train it on 6 bands, I can train it on 6 LSST bands plus Atlas data bands or like ZTF bands. So that's still something in the works. I envision something like this could and would work for that as well, where if you have, say, 2 points from Atlas and like 7 from, I don't know much about Atlas, so I could be wrong. I don't know how many points I have, but like a few points from Atlas, few from LSST, and you can have still a coherent picture. And so I think for multi-wavelength as well, it should be doable. Thank you.
Thanks, Sid. Thanks for the nice talk. I'm wondering if you could elaborate a little bit more on the input and the training time. So I understand you're training with models, which are going to be intrinsically uncertain, but then also one of the reasons that people like Gaussian processes is because they're principled uncertainties, whereas a neural process generally doesn't. So could you elaborate a bit more on that?
Yes, I have some. So this is a figure I have in the paper. So we were looking at calibration, where, of course, this uncertainty is model-based. But unlike regular neural networks, neural processes are much better at doing a reasonable job. So here I'm looking at sort of predicted uncertainty versus sort of real, like predicted error bars versus real error bars, and how often the data falls outside of that. And we see that, at least on the simulated data set, it does better than sort of all the other methods, including Gaussian process as well. But this, again, does not really compare to real sort of Bayesian MCMC methods in some sense. And so that is a test I'm still like taking a look at. But I think there is a way to calibrate it even better and trust it. And what was your second question? Sorry. Yes, so in terms of, I'm just using this diverse data set. I'm not really doing a principled way of adding any uncertainties. But the way I train it is sort of like an autoencoder approach, where I ask it to reconstruct. It's with a negative log likelihood. So as long as it is within an error margin, it sort of learns. And there's some more literature on the ML side of things, where they incorporate a latent attention, but that's very specific, and we can talk later. But that's the basic answer.
Two last question, Ramandeep, and after.
Okay, very nice talk. I have a very naive question. I'm wondering, no, in all the examples that you shown today, no physics was constrained in terms of the parameters, and the light curves are rather simple, and one can produce those, especially for supernovae, from a given model, let's say. I'm wondering, why is there a need to reconstruct the light curve, given the data you showed? Why can't I just simply fit the physical models themselves and just be done with it?
Right, because you don't know what kind of class you will have. And with the data volumes you're looking at, if you try to fit each and every single light curve, you will not be able to do that. And so we want some quick sort of approach to just sift through the data set. And this is a good visual way as well, where you can have transformer classifiers making predictions, but you can't really look at the light curve. And it's like, okay, it might still work, but how does it work is a bit uncertain. So here you get within seconds, you get like a prediction of what the full light curve would look like. And I expect this to be used live as you keep collecting more data points with LSST. So as you keep getting more data, your prediction improves, and you can look at the light curve. And then if you find something that's a class you want, then you can use your own models and get a better physical driven model.
The very last question.
If you wanted to add a new transient class, how many examples roughly do you think you would need in the training data set?
Good question. So this is something still I'm playing with. For dense cadence training, I've been taking sort of like these roughly 1,000 light curves with dense cadence. But on fine tuning, I just took, I think, around 1,000 light curves, but LSST-like cadence, so many less number of points. And so still something I'm playing with, but I think between a few hundreds and thousands should work. And if you can simulate it, that sort of adds a good prior. But if you can't, even then fine-tuning, because it has already learned the shape, should be possible. So still, it's not something I've taken a look at. And if you have data, I'll be happy to throw it in as well.
Okay, we can thank again.
Thank you.
So you are the winner. The number of questions.
I will not be getting that many questions.
Non, je vois pas. Oui. Lorraine, yes.
Yeah.
Comme de good luck. It should work. 15 minutes.
Okay.
Number of questions.
Okay, awesome. So thank you, everyone. Hi, my name's Lauren. I'm a research fellow at McGill University. Before that, I was at Oxford, where I did my PhD and my first postdoc, and that is where the work that I'm going to talk to you guys about today started. So this, all the words will make sense, hopefully, by the end of the talk. But this is not work that I've done on my own. This is part of a large group of people, well, a relatively large group of people who have been working on this telescope and on these observations since before I started my PhD. But in particular, I want to highlight the work of two undergrads that have been working with me at McGill this year. Over the past year, they have learned how to learn about gamma ray burst models. They've learned how to fit to data. It's just absolutely been incredible that these two are undergrads. So these are my two undergrads, Dina and Adrien, and I just wanted to highlight the work the contributions that they have made to this project. Now, we've had about 3 or 4 GRB talks already today, and we haven't seen a version of this plot, which I think is quite impressive. This is well, it's not my version, it is my student Elliot's updated version. He makes really beautiful schematics, so I wanted to include that. So in gamma ray bursts, we have, and what I'm going to be talking about today is majoritively traditional long collapsar GRBs, okay? And so they're produced by collapsing massive stars. We see the prompt emission, and for me, the prompt emission is great, super great, but not what I'm interested in studying. It just tells me where to point the telescope, okay? The part I'm interested in is the afterglow. That is obviously what comes afterwards. And it's produced by interaction between the circumstellar environment and the relativistic jet that's been launched. Now, in particular, I'm going to talk about the radio part, so that's not really been mentioned so far today. So hopefully I can teach everyone some new and interesting things. Now, in terms of the radio, the picture, I think we, certainly in the GRB community, we all think is a little bit more complicated. So I just want to briefly talk about what we kind of expect to see. Okay, so on the left-hand side here, we have 2 different example SEDs for what we could expect to see in the radio band or across the radio band for a gamma ray burst, okay? These examples are actually taken from my work on GRB 221009A, i.e. the boat, so that it's real data. This is what forward shock, traditional jet circumstellar interaction SEDs can look like at 2 different time steps. So we have one that's pretty early on, maybe a couple days, and then we have one later at 100 days. And then on the right-hand side here, we have light curves at 2 different observing frequencies. So one may be closer to 100 gigahertz, one may be more like 5 to 15 gigahertz. And you see, I've drawn these little horizontal, vertical dashed lines. These correspond to different synchrotron breaks passing, sitting at different wavelengths or passing through the observing band, is what we see on the right-hand side here. Now, this is cool. This is quite nice and easy. We could take observations at different frequencies and constrain all of this. But in reality, a lot of the time, we're not just observing one single shock component. With any forward shock propagating out into the circumstellar environment, you're going to have a corresponding reverse shock that's also moving back. And now, so in reality, it could look more something like this. But the relative brightnesses of the different shock components and the relative velocities of the evolution is very dependent on the jet physics and the circumstellar environment. So whilst this is one example of what your SEDs could look like and what your light curves could look like, in reality, this is going to be hugely variable. And so what we want to kind of do as what I want to do as a radio astronomer is kind of work out a way in which we can best deconstruct these different components and get the most physics out of these systems. And there's many different ways of doing this. The way I'm going to talk today is just one version. And it's a version using this absolutely incredible radio telescope that is in Cambridge in the United Kingdom. So the telescope is the Arc-Minute Microkelvin Imager Large Array. It's very catchy, I know. There's also a small array, which is why there is the title Large Array. And originally, Amy did a lot of cosmology. But over the years, it's become more dedicated to doing transient science, and it's done an absolutely phenomenal job. So it's made of 8 dishes. You can see all 8 of them here. They're actually built on like a train track, so they could originally move out and in, which is really cool. It observes at a central frequency of 15.5 gigahertz. And observes with a 5 gigahertz bandwidth. So if we have higher signal to noise observations, we can split our data up. Otherwise, we just have the improved sensitivity of this wider bandwidth. Now, one of the amazing things that Amy has done and has pioneered in the radio regime is this alarm program. Now, this is a rapid response observing program, which in the way that many optical facilities already do, it takes the information from, say, well, for us, for the Swift telescope, and it allows automatic repointing of the telescope. Now, this is very rare in the radio, but this was pioneered by something my predecessor and now collaborator Gemma Anderson did with her collaborators. And it has allowed basically immediate repointing of the telescope. We can get on source and get detection sometimes in a couple of minutes. And yeah, so it's great because it enables us to place constraints on the earliest possible radio emission. Now, the catalog that I'm working on, Amy has been collecting data in this format for many years, and there is a previous radio GLB afterglow catalog that does in fact exist, written by Gemma and was published back in 2018. But the group of events that I'm talking about were between January of 2016 and January of 2025. With a gap, obviously, in there for COVID. No one was taking really observations during the pandemic, I think, and we were no different from everyone else. So I started my PhD in 2018, so these observations predate me in some capacity. But in total, we have 210 gamma ray bursts in this sample, with a total of 1,035 observations in total. Now, with the exception of one burst, I reduced all of these observations, and I do not recommend trying to repeat that. It was not fun. This has been a large component of my life for the last 8 years. On average, we reach a noise limit of around 0.2 millijanskis. For people who work on radio observations, this might not seem particularly deep, especially when we consider facilities such as the VLA. But what I will show on the next slide, I hope will convince you that otherwise this is, despite having this slightly less deep sensitivity, we can still do some really awesome science. Now, in total, out of 210 events, we detect 37 radio counterparts at the position of GLBs. I've called it afterglows here, but there's a couple of cases where we don't have sufficient data to really say if something is variable. So it could be host galaxy or contamination emission. Of these 37, we've already published 5. These have already been published by myself or my collaborator, Joe Bright. But as I'm sure we all can understand, a lot of the time we are people power limited. And so I don't know about you, but I don't think in the past 8 years, any of us could have published 37 papers each on individual gamma ray bursts. I also don't just work on gamma ray bursts, so I've been doing other things with my time as well. And of our 210, 49 have redshifts. So this means we can look at not only the flux density evolution of these bursts, but we can look at them in luminosity space as well. So when I was collating this catalog, I was like, how do we present 210 bursts, okay? And so I decided to make what I think is the ugliest plot I've ever made. And it is this one. I'm sorry if it's kind of horrible to look at, but it's also kind of cool. It was much worse. The first iteration, there was no colors. It was really, really ugly. And so what we have here is the flux density as a function of time for the central point of each observation, okay? And all the different colors correspond to different detected bursts. Obviously, we have the boat here reaching about 40 millijanskis, and then many others that sit kind of more around the noise limit of the telescope. But one of the things that is the reason this is such a hideous plot, maybe compared to if, say, you took like a collection of X-ray afterglows or something, is because the peak time scale at which afterglows reach in the radio is so much more varied than what we can expect. And this harks back to those original sample SEDs I showed where we could have like reverse shocks plus forward shocks, and it really affects what the observations were, how our observations evolve with time. We actually find that like if we take the peaks of the different afterglows we do detect, we get a pretty flat distribution in the time of the light curve peaks from pre like 0.1 days or pre 1 day post burst out to about a few tens of days. So that's really interesting in trying to see if there are different populations, if we're trying to really interpret what's going on here. And so if we collapse that previous plot down in flux density space and we show just this as a histogram in terms of our number of detections and non-detections as a function of time, we can also see some interesting things, okay? You can see, unfortunately, we do not detect many afterglows in the first day post-burst. So despite having this incredible alarm program, we do not detect many things. But it starts our observing cadence for each event, okay? So for all our gamma ray bursts, or for the majority of our gamma ray bursts, we try to keep a logarithmic observing campaign going from as early as possible post-burst out to like maybe like 15 to 30 days. And so you can see as a function of time, our detection rate increases as to be expected as we detect more and more of these events. But after about 30 days, it kind of plateaus off a little bit. But okay, it's kind of sad that we didn't detect loads of like events in the first 1 day post burst, but that doesn't mean that this is not worthwhile science. We've seen with ACCA, we have seen with other facilities such as the SMA. They've recently published an event. Yeah, thanks. That we are able to detect radio emission in the first day or first hours or even first minutes post burst for some of these gamma ray bursts. And so Amy really has like pioneered this component. And without some of these, we wouldn't have detected 130427A, which is an incredibly famous gamma ray burst that we got on source within a couple of hours with Amy. Now, in the last couple of minutes, I just want to put this a little bit more in context and not just look in flux density space, but look in luminosity space as well. So for the, I think I said 47? For the 47 events for which we have redshifts, this is what our detections and non-detections look like as a function of redshift. And so you can see we aren't really, we're pretty insensitive to the redshift of these bursts, which is kind of interesting. Honestly, before I made this plot, I was like, oh, we're just going to be detecting things for like below redshift 1. And that doesn't really seem to be the case, which I think is really interesting. But I think it becomes more obvious when we look at the light curves in luminosity space as well. So that's, this is actually just my last plot before my conclusions. So this is all of our events in luminosity space, okay? And you can see there's a huge range of luminosities that we're seeing here, okay? So we're spanning about 5 orders of magnitude in luminosity, which is larger than what we see at optical and X-ray wavelengths as well. And again, this is because of what I was talking about earlier. We have these multiple emission regions. They're evolving at different timescales. You might sometimes have like 2 whoppingly bright like a reverse and forward shock, or sometimes you just kind of have like a piddly little forward shock chilling. So it's we're really seeing what such a huge range of radio properties we can get from a single facility, and I think that's something that the Amy telescope has done really amazingly over the last decade. So I think I finished a little early, which is pretty impressive for me. I usually run over, but in my last couple minutes, I just want to summarize my takeaways for this talk, and saying that one of, which is a thing that I haven't actually mentioned so far, is that, okay, whilst Amy is not the world's most sensitive radio facility, what is absolutely fantastic in what it has done is collecting high cadence light curves for a huge range of transients, okay? This has not just been the case for gamma ray bursts, we have been doing it for X-ray binaries, TDEs, and supernovae as well, as I'm sure I hope many of you have been reading the Amy papers over the last decade or so. We also found, and this is talked about more in the paper, that in the cases where we're able to do this more detailed analysis, we find that reverse shocks are very, very common at our observing frequencies on much longer timescales than people kind of write about in the introductions to our papers. As I've already said, our radio detections seem to be pretty redshift insensitive. And one thing that I haven't written up here, but I do want to say, is that when this paper comes out, I am like furiously writing right now ahead of job season happening starting in the next month or so. is that all the data that goes into this catalog is going to be made publicly available online for anyone to use. So my students, Adrien and Dina, part of what they've been doing over the last year is creating a website that will enable you to download all of the data in CSV format and really make it accessible. Because, I mean, many of these bursts that we've been detecting with like at high cadence, there aren't papers out there looking at other wavelengths. So what I hope and what I imagine is the case is that many of you guys have maybe some data at some other wavelength for bursts that we also have data. And so you guys can use this and maybe get some more papers coming out and some more really interesting studies of GRB afterglows. So hopefully the paper should be out in the next month, fingers crossed. And with that, I would like to say thank you. And if anyone has any questions, I'd be happy to answer them.
Oh, okay. I stop.
So how is the scintillation? How much affecting scintillation affecting the observation?
Yeah, so we see it. So just in the 6 cases that we like do the detailed analysis here, we see pretty strong scintillation. Well, for 15 gigahertz, strong scintillation in 2 cases. So we see an amplitude modulation of about 30%. And so what? 2 and 6, 30% of the time we're seeing it. There's a number of other cases in the past where we've published that we also see scintillation, which I think is, I mean, to me, it was kind of surprising that it would be so strong at 15 gigahertz because everyone's like, oh, above 10, you're not expecting to see scintillation. And yeah, so we talk a little bit about that in the paper as well and do some like basic analysis of like source sizes and things. One of the things that is interesting, so in this data set, we have the afterglow for 20, it's already been mentioned. It had the wild optical afterglow light curve. I think Susanna presented it. We see scintillation in that case, and we see it out to like tens of days. Like it covers our whole light curve. So yeah, we see some kind of interesting stuff. It's okay.
Okay.
Wait.
Yeah, hopefully that was one of my 2 questions, so I only have one question now. Can you say a little bit more about the reverse shock? Because canonically, reverse shock was this thing that comes in the first day and then it fades. But in your detection statistics, you show that your detections are pretty sparse in the first few days and then more common later on. But you also say reverse shocks are common. So how do we put all these things together?
Yeah, so I think this is something that we see as a result of having like really good light curves rather than really good spectral coverage. That we're able to see these like changes in the light curves that infers that we have these like dominant reverse shocks. And so in terms of like the peak timescales that we're seeing, anything that peaks before 10 days, we're saying is like our analysis shows that it's more likely to be a reverse shock. Obviously, other people can interpret the data in other ways they like. But I would say, in terms of the cases,
early jet break, right? Potentially, if it's before 10 days.
So we only see one case of a traditional jet break, which I think is due to, like, in most cases, us being close to self-absorption break, like, affects things a little bit. But the reverse shocks, I would say we see some evidence of reverse shock with Amy, like, on the order of 50% of the time. These are not something that's, like, hardly ever there. And they're dominant for, like, a couple of days, like, up to, say, 10 days, of which case the forward shock can take over. Like, if we see a peak after 10 days, that's forward shock. But I think in my mind, it has shown that I need to like change my wording of how I write about reverse shocks, that I'm like, okay, like 221009 and 190829A were not these like special cases of long-lived reverse shocks. This is happening way more often than we think. Does that answer your question?
Yeah, more or less, yeah.
Yeah, okay.
Talk more or less.
A quick question. Did you do any polarimetry, or can you do polarimetry?
We can't do polarimetry, unfortunately. But this is, I'm going to take this as a thing. So one of the really sad things is that as the radio community moves forward, we're moving more towards this like system where we have very large, very sensitive, but very centralized telescope programs. So for example, the SKA and GVLA, and these are incredible for so many things and can do incredible stuff for transient science. But I think what we need to do also as a transient community to continue to do awesome science like this is need to support smaller facilities that can do dedicated transient science. So we already have systems like that are being built, like the Africa Millimeter Telescope, that will do stuff. This will do polarimetry at much higher frequencies. But I think if we want to do stuff like this and be able to get really, really good data, we need to be able to like have these smaller, more flexible facilities, because I would love to learn more about polarization and I'm trying to get it in on my programs, but it's obviously very hard to do. Yeah. Sorry, hi.
What are the differences do you see between the radio afterglows of short GRBs and long GRBs?
So with Amy, we have never detected a short GRB afterglow. There's a paper led by Genevieve Schroeder, and I'm the second author on GRB 21. Sorry.
12
Yeah, in which we have like pretty strong upper limits, but short GRBs are traditionally much fainter, and they're just sitting below our sensitivity limit. But we're in terms of like radio studies on short GRBs I've done, we're seeing far more varied behavior, even more so than what we're seeing for long GRBs. If you want to see some like wacky like radio light curves, I would certainly recommend looking at like cosmological short GRBs. Atka and Meerkat are finding some really cool stuff. That's okay.
So just a quick question, if I may have the time. So I love the project, and I love the fact that that you can do systematic studies with Amy. I was wondering how systematic you have been in the triggering in order to do then systematic studies of all those percentage of bursts with reverse shock or whatever you want to go for.
So pre-COVID, no. So pre-COVID, our rapid response program was like fully automated. I would just like get to work next day and I'd be like, oh, look, we observed something new. That's really fun. And then we'd like manually schedule the following observations. Unfortunately, since the pandemic, we had to remove the system because it was, Amy is a very old telescope. And so we had to remove this to keep the at the like thing of keeping the telescope running. And I was then implementing the scheduling myself, and we tried to do this as regularly as possible. Obviously, I am only a person. I am not perfect. And so there were like failures in this respect. But we talk about this in the paper as well, about how like important this has been in terms of like, our systematic program and things like that. Yeah. But the like 2015 to like 2019, it was like spot on. It was incredible, which is why there's like in my light curves, there was like a weird vertical line of like upper limits at about what corresponds to 1 hour post burst. And that was just all of our like rapid response programs. I'm so sorry. Someone else needs to talk. Sorry.
Okay, we thank you again.
Peter? And now we host Dylan.
There is the pointer? Oh, yes, here. And how does it work? Okay, perfect. Okay, so is it good? Okay. I start. Okay. So hello everybody. My name is Dylan. I'm a PhD student in CEA, and I'm working with Damien on a project about transients that are jointly detected by EP and SVOM. And I will focus more on the example of GRB 241130b, as it was our test case for our analysis. So first, I want a little bit of context for those who don't know. But so when I'm speaking about transients that are jointly detected by both missions, I mean the transients that have been detected by EPWXT and either by SVOM Eclair or GRM or by both. So here you have a slide where I summarize the qualities of each instrument. EPWXT, I will just go quick, but EPWXT, it's an instrument that operates in the range of 0.5 to 4 kV, whereas Eclair, it's at the continuity, it's at 4 to 120 kV, and then you have GRM that goes from few kVs to MeVs. In terms of sensitivity, so you have EPWXT that is as 0.5 times 10 at the power minus 10 erg per second per centimeter square. With a field of view that is around 1 steradian. And for Eclair, it is a rule of thumb, but the rule of thumb is to say that the sensitivity is 100 times less than the one of EPWXT, but for a field of view that is 2 times larger. And for for SVOM GRM, sorry, The sensitivity is 100 times less than the one of Eclair, but with a field of view that is around 2.6 steradian. So for this analysis, we focus more on the prompt emission these times. And here you have the perfect case of what we want. When we want a transient that is detected by both missions, we want that we see the beginning and the end of the emission. We see everything. However, of course, this is the perfect case, but the world is not perfect, and we have some limitation. Even though both missions have the same orbit, as you can see, we have problem, of course, due to operation. There is the Earth occultation. You can have one instrument that is Earth occulted, whereas the other mission is not. You have, of course, the SAE passage. One instrument one mission as an instrument completely switched off due to SAE, but not the other. You have also a different pointing strategy, which means that they are not looking always at the same part of the skies. And you have also slew. This is a big effect for EPWXT because when EPWXT is slewing, the source goes from optics to optics, and so you are no more able to reconstruct the light curve of it. So it can cause problem, and it will truncate your light curve. So now, in terms of statistics between the two missions, the joint observation, so after 2 years of SVOM, we have a total transient number that is about 30. Detected by EP and SVOM, and for a rate that is around 1.2 per month. So what does it mean? It means that if we extrapolate those numbers for 5 years, we should have something around 70 transients jointly detected by both missions. Me, personally, I focus on these samples, the one, sorry, but it's cut by the bar, but basically it goes from August 2024 to October of last year, 2025, of transients jointly detected by both missions. And so the total number is 50. And as I said, due to the overall effect of the operation, you discard already 6 because there was a slew in EPWXT, and you have other 5 that you discard because you have Earth occultation or difference pointing. Basically, EP was not on the target at the moment of the prompt emission and just came late or just flew to a different location. And so in total, you have only 6, so 40% out of the 15 that are well characterized and for which you have the beginning of the prompt and the end. So now if we took back the numbers that I gave you for the 5 years with this correction, you end up more with 28 of those transients that should be well characterized by both missions. So now you may ask, why do we care about joint observation of both with both missions? First, because it gives you an incredible sample of the spectrum over 40K of energy, from 4 kV to few MeVs. Also, if you are interested, because you have this wide range, spectral range, you can try to find breaks inside of the spectrum. And in that case, for this paper, for example, low energy breaks and what happens between the breaks and the epoch usually correspond to synchrotron emission. And this is something you can verify if you have a joint observation with both missions. And you can also, there was one question about it, about the duration between EP and SVOM ingredients earlier, between EP and gamma rays. Basically, for gamma ray bursts, you expect that they follow more or less this relation, this duration versus energy relation. And what it told you is that the size of the pulse, the width of the pulse, should be with respect to the energy. You should have exponent that should be around minus 0.3 to 0.5. This is what I've been found in the Battiera. It has also been found at higher energy with GBM by Bissadi et al. 2011. So this is what we wanted to test. So here is the example of GRB 241113b. So opposite to what we saw prior, for this burst at least, we have this duration versus energy relation, or T90, it's the same, that is respected. We have an exponent that is around minus 0.35. So it does not, what we saw earlier for a burst of EP that was maybe 100 times longer for EPWXT than gamma ray instruments is not, let's say, the rules. And actually, this burst follow well this relation. For the spectral analysis, it's a bit more difficult. So this GRB 1113b is an XRF, so it means that it's soft, but also that is unfortunately a little bit faint. And if we look at the EPWXT independent fits, we find that it should have alpha around minus 2.7, so it should be a very soft event. However, when we do the joint fit between the gamma ray instruments and WXT, what we find is an alpha that is more, let's say, compatible with what we usually expect for gamma ray burst, and also that is around 1, so less soft than what have been shown by EPWXT. This is, let's say, a more or less non-biased, because with EPWXT, you have this very tight energy band that goes from 0.5 to 4 kV. And so what happens is that half of this band is actually hidden by the absorption. And so when you are trying to fit, you are trying to fit both the absorption, but also a component like a power law. And the high energy part, you don't have enough leverage. And so you end up with huge uncertainty on this, and it can bias usually to a lower energy. And what's happened is that the gamma rays help you to give more leverage on this quantity and to constrain it more. So now the location of this GRB into the amateur relation, you can find this is the green track, that it is follow nicely the amateur relation. That is it is not an outlier of it, and that basically this is one argument for us, but that's the scenario for it should not be, let's say, too crazy, too wide to explain its energy, because it does not deviate too much from this relation. And so at the end, in terms of conclusion, GRB 241113b, we've made some tests. We know that it is not a shock breakout event. It does not also come from an off-axis jet that is viewed off-axis. And also that that it is not a dirty fireball, because we found a Burger chlorine factor that was around 100, so very classical in terms of GRB and for its afterglow. So we think that this burst actually is a good example of a soft burst, but for which the interpretation, the scenario, should be intrinsic of the jet. Maybe it's because there is the contrast between the shell that form the internal shock. Maybe the contrast is not that high in terms of Lorentz factor. Maybe the photosphere, it's due to a photospheric emission or the presence of a hot cocoon, but we discarded the scenario that I mentioned above. And in general, for SVOM and EP population, what does it mean? It means that we should have 70 transients jointly detected by both missions, but 28 of them should be well characterized to completely study the prompt emission of it. With both missions, we can well characterize the prompt emission up to over 4 decades in energy, 4 decades of energy, and let's say this is one of the arguments that I want you to remember, is that unfortunately, and we will benefit much more by having those instruments, EPWXT, Eclair, but also GRM on the same platform, because we will avoid all the problem I spoke about, and we'll be able to characterize the prompt emission on those this wide energy range systematically. And this is to remember that the study is still ongoing. So if you have any comments, any contribution that you would like to add, this is more than welcome. And thank you.
Thanks. Can you go back to your Amati relation plot?
Yes.
That you showed earlier. So on Susanna's plot that she showed on the SVOM events only, there are a bunch of things in the bottom right in this X-ray rich regime.
Yeah.
Are any of those with EP detections? How should we be thinking about those events in the broader space?
So on the broader space, I have slides for it. So you can find that the one that deviates far from the Amati relation, usually have also some kind of, as I said, crazy scenario behind, like a fake jet, off-axis jet, very off-axis, or a canonical dirty fireball. This is not the case for the burst at ratio, but this is what we see with EP in general. So yeah, there is some kinds of events.
There is one. Okay, which one is that? Okay.
Other question, comment? No? Okay, I think that's all. We can thank you again, Dylan. Okay, now we have a series of flash talk. I suggest that all the speakers are coming. Like this, it will be. Yes, Kira, Aleksandra, Filip, Bugli. You can organize as you want, huh? Ouais, c'est ça. You have 2 minutes.
Okay. Good afternoon, everyone. My name is Kira. I'm a PhD student at the University of Cape Town. One of my supervisors is Professor Ben Stappers, who's also here this week. And my poster is on searching the image domain for radio transients in the Magellanic Clouds. A class of objects that we're particularly interested in is long period transients, or LPTs, which are transients with periods that range from tens of seconds to hours. All of those discovered so far are galactic sources, and some appear to be from isolated neutron stars. Others are from white dwarf binaries, and a few are from unknown sources, which means we need to find more of them. The reason we are specifically looking in the Magellanic Clouds is because they offer a differing environment to that of the Milky Way, but they're still close enough that we should be able to see LPTs if they are indeed there. To do this, we're using Meerkat, which is a radio interferometer in South Africa, and then for optical follow-up, we're using Meerlicht, which is also in South Africa. These two telescopes can also observe simultaneously, and they're well located to observe the Magellanic Clouds from the southern hemisphere. Then more specifically, how we're finding these transients is we are imaging the radio data and getting short timescale snapshots and looking for sources that seem to turn on and off from snapshot to snapshot. So if that sounds interesting to you, or you want to know more about the telescopes we're using, or exactly how we're doing that, or anything we found so far, then please come and chat to me.
Let's change. 1 second. Ah, bon. Benjamin, au secours. Donc c'est... Qu'est-ce qu'il m'a fait là? Ah. Ok. C'est le professionnel.
Hi, everybody. I'm Aleksandra Bochenek, or Ola. I'm a third-year PhD student at the Liverpool John Moores University. My supervisor is Dan Pelly, and I work on the automated follow-up sample of GRB afterglows, of Swift GRB afterglows with the Palomar 60-inch telescope. So the sample consists of bursts follow-up within 1 hour of Swift trigger. The full data is 87 bursts. The final sample is 74 after some data quality cuts. And because it's an automated follow-up sample, it minimizes human selection bias, so we can reflect the Swift selection function. We focus on calculating rates and basic characteristics of the afterglows. We can probe very early afterglow behavior, so we can see the plots of optical and XRT joint light curves here. We characterize decay and spectral indices, distributions, but we also characterize variability rates of the afterglows. We calculate the luminosity function at 1,000 seconds post-Rüge. We corrected for, you can see that here, we corrected for redshift selection effects because whilst the sample, the follow-up is unbiased, the redshift availability isn't. We calculate things like the dark bursts ratio. We can probe the environment of the bursts. So we get 33% at least of our sample to be dark bursts, up to 45%. We can characterize some energetics of the bursts, looking at things, for example, as the isotropic equivalent energies, but we aim to characterize them further with modeling and get also describe the jet structure, opening angles, and velocities of the bursts. So not all of this is going to be on a poster because that's quite a lot of sample data, but please come look at the poster and come to talk to me. Yeah, thank you.
Je vais try. Bon, Benjamin, viens, parce que là, il m'énerve ton truc.
We'll be good at this soon.
I'm fighting with this computer. C'est lequel? Too painful.
Thank you. All right. Hello, everyone. My name is Shar Daniels. I'm a PhD candidate at the University of Delaware in the United States. I work with Dr. Federica Bianco, who will be here tomorrow, in case you want to talk to her. I also am the FAST transient subgroup coordinator for the Transient Variable Science Collaboration for the Rubin Observatory, which did take its first it began its thing last week. So I'm happy to talk to you about that as well. But the poster I brought to the conference this week is about this very unusual but kind of exciting way to find optical transients that are very fast, like we're talking millisecond timescales. My data is actually the background of this poster. So instead of it looking like stars up in the sky, we have these streaks, which is essentially a time series. And if you want to know exactly how we got from stars to this streak time series using the Zwicky Transient Facility Normal Optical Telescope in California, come talk to me at my poster. I have built a whole pipeline to extract brightening and dimming events on these timescales. And I also am presenting a few possible transient candidates, which you can come look at for yourself to decide whether you think they're real or not. So thank you.
Thank you. Two last one. Huh?
Hi everyone, my name is Runduo Liang from NAOC, and my supervisor is Professor Weimin Yuan. My talk is about optical counterpart search for fast X-ray transients by EP. As we know, we have low latency straight alert stream for EP transients with autonomous follow-up observations and better localization. But there are much more sources which is sub-threshold without the follow-up observations. And in addition, some transients like TDE or supernovae, they has longer time delay for the emergence of optical emission. So our work is aiming to discover and identify the optical counterpart using the wide field survey data. So we started from archival data mining. We construct a X-ray source sample from EP, and here's the sky distribution of that. We then perform a spatial and a temporal cross-match with the optical data. We identify some candidates, but most of them are chance coincidence. But surprisingly, we identify one candidates EP240506A and the counterpart AT2024FS, which was initially missed out by the TO observations. And optical emission was discovered by GTF and Pan-STARRS in 8 days from their survey. We also identified UV emission in 2 days at the position of the transients. And here's the light curve of in X-ray and optical. In a word, the X-ray is consistent with a low luminosity GRB, and the optical data can reproduced by a supernova model with ejected mass about 2.5 solar mass. And then we move forward to real-time search on mid-August last year. 55 candidates identified so far, including some GRBs, supernovae, TDE, and Adriens, but most of them are still unclassified due to the lack of follow-up observations and better localizations. And here's the histogram is the the distribution of the time delay. We can model it with a Gaussian and a plus uniform distribution, and then we can constrain the F real, which representing the fraction of real candidates to be 0.4, which means there are more real candidates in the unknown match. And I also want to highlight one case, EP260518A, which there's subthreshold detection by EP and as well as by SVOM. We performed some follow-up observations, and this is a GRB with a standard afterglow. But I think this might be a benchmark because we discovered a transient and its counterpart without any EP alerts and SVOM or any other GRB satellite alerts. So in conclusion, our work is maximizing the discovery of the diversity and the number of the FXT and its counterpart and enriching its population. So if you are interested in more details, you can come to my poster and discuss with me. So thanks for your attention.
Hello, everybody. Originally, I was meant to talk about how we achieve sub-minute reaction time for GRB alerts and are able to detect their afterglow as fast as possible. But as none of my supervisors and collaborators from Italy are here, I decided to talk about this exciting GRB that we detected recently, and published in Astronomy and Astrophysics. So, as most of you know, the distribution of electrons within GRB afterglow are usually described by this simple power law. But Dimitrios Gianninos, in his paper from 2009, used this thermal tail of those electrons that then propagates into the spectrum in this way. Here, the delta means fractions of thermal electrons in the GRB electron population, and we think that on the 2nd of July of 2005, we saw this population as this, we call it fluffy bump in this GRB afterglow, this being normal flare. And with our colleagues in Italy, we've managed to model this thing. And as you can see that initially, the first flare is just a normal flare or like tail of the prompt emission, Whereas this crossing of this thermal population that radiates synchrotron emission is seen just in the optical and is disconnected from the X-ray emission. So, but as we saw it here, and we saw it in some other GRB candidates that we are preparing for bigger paper, because this was later in astronomy astrophysics. In this publication, they claim that signature of this thermal population could be visible by other instruments. So if you have early data in the optical for some of the candidates that we've identified, this bump might be and like this bump is visible only in the low P cases, so it might be interesting to explore as well. And I invite you to check out this paper. This is my supervisor. This is me, and I will not distract you much further. The only thing that I'll also mention that online here is my colleague from QVIC, and as Czech Republic is a small country, we are also preparing UV mission. So thank you. And check the paper, check the poster.
Thank you very much. Okay. There is the last one, the very last one, online.
Hi, thank you. Can you hear me?
Okay. Yeah. We see.
Okay, thank you. Awesome.
Share your screen.
I assume you projected your slides because I sent you the PDF, but I can share the script.
Right. Okay.
Yeah.
Let's go. I thought you wanted.
Okay. Hello. I will just start the voiceover. Thank you everyone for being here. My name is Matteo Bugli. I'm a researcher.
One second.
Okay.
Plus
Sorry.
the time to
Yeah.
share this. Voilà. You can go.
Okay, thank you. I'm Matteo Bugli. I'm a researcher at the Astrophysics Department of CEA Saclay, and I'm presenting you the work done by my student Andrea Gelati as a master student at the University of Florence. Now he's doing a PhD thesis in Florence as well, working on magnetic-rotational Coriolis supernovae. So the most extreme case of Coriolis having fast rotation and strong magnetic fields. And the core question of his work was the assessing the impact of the nuclear equational state. So how nuclear dense matter and how we describe it in the simulation affects the results. So here in the yellow box, you can see the properties of the progenitor that we studied. So a typical Coriolis model with a very massive iron core, on top of which we overlapped strong rotation and intense magnetic fields, and Andrea performed simulations using a relativistic MHD code NOS-ALCAR with sophisticated neutrino transport. You can see also a summary of the different equational state for in total that we considered, and on the plot just on the right, the mass radius diagram that gives you a sense of how stiff these equational states are. So they differ from many different parameters, but in our work and the results that you can see on the bottom layer, we tracked the multifaceted impact that nuclear density matter have on many different aspects of the explosion. First and foremost, the formation of the proton-neutron star, this PNS, and you can see in the top, in the bottom left green box, the moment of inertia of the proton-neutron star. So there is a different distribution of mass and rotation, which has a direct impact on how the explosion efficiency comes by, because these different degrees of compressibility means that magnetic fields are amplified in a different way, and also the angular momentum is transported differently. So this is a direct impact on the explosion. On the middle panel, you can see the early emission of gravitational waves. So you can see how the bounce signal at the 0 millisecond mark, it's basically identical. But once we go a bit further, the first tenth of a second, the prompt convection signal is very different between the equational states. And last but not least, in the last panel, the composition of the ejecta, so the electron fraction on the jet, you can see how at low YE there is a definite difference between different equational states depending on how prompt the explosion was. And since these nucleosynthetic calculations are so sensitive to YE, we expect these to actually have an impact of the amount of, for instance, our process elements produced during these explosions. I'll leave you with the summary. The prospects are, of course, more progenitor, more equational state, and of course 3D, which is crucial. Feel free to contact either me or Andrea by email and check out the poster online. Thank you for your attention.